In this video, we're going to look at another example of implicit differentiation. In this case, we're going to be looking at x equals y squared, which is the sideways parabola. And it is interesting because it is not a function again. It is the parabola that has a top arch, like so, but it also goes down to a bottom arch as well, like that. This entire curve is defined by y squared equals x. And of course it's not a function because if you pick an x value, there are at least two y values, well, specifically two y values in this case, that you can get back. So it doesn't pass the vertical line, or it fails the vertical line test, so it's not a function. However, again, we should be able to define the slope at a point and talk about then the equation of a tangent line. That should all be stuff that we can do. So how do we do that? We start with our relationship. This is a relationship that's always true, and if that's the case, then its rate of change with respect to x on the left-hand side and the right-hand side should also be equal. So I usually phrase this as take the x derivative, or take d dx, of both sides. When we do that, I'll be explicit again here. When we take the x derivative, we get dx dx. Y squared, the derivative of anything squared, is 2, the same thing to the power 1, then times the derivative of the inside. And what we can then simplify is dx dx is just 1. The x derivative of x is 1, and everything else here we can tidy up a little bit further and get dy dx by itself. This again is our formula for slopes. Once we have that, we can now solve for it and actually get the formula for slopes isolated, and all it's going to require is bringing the 2y into the denominator on the other side. So that is going to give us our slope formula. On the next page, we'll actually follow that up by finding the equation of the tangent line, not just the slope, but the full equation at the point 4, 2. All right, so at the point 4, 2, we're going to have dy dx equals 1 over 2 times the y value, and the y value is the 2, so 1/4. With the tangent line then, the tangent line is a y equals, and I'm going to make this very generic. I'm not going to use m or anything else. I'm going to use slope x minus a plus c. Sometimes this is called the x naught, sometimes this is called the y naught. It's the root point, or the point that we're drawing our graph through. In our specific case here, that's x minus the 4 value, that's our a or x naught, and that's our c or y naught. And so we get x minus 4 plus the 2, and the slope value that we need is the dy dx, so 1/4 of that. That y value is going to be the formula for a tangent line to the graph x equals y squared, which is not a function, but is the sideways parabola. We can confirm that loosely based on our sketch here. It won't be quite as convincing as a computer-generated graph, but by looking at the slope and knowing that each of these squares is 2 squares here is 1 unit, then if we have a slope of 1/4, that means going across 1 goes up half of this, and then going up 2 takes us 1 full square. And indeed, that seems to match quite nicely with our sketch. So this green line would be our tangent line at the point 4, 2, and it seems very well described by our formula 1/4 x minus 4 plus 2. So that's another example of starting with a relationship that's not a function, but still being able to compute a formula for slopes and use that with our earlier work to define the formula for a tangent line. A very powerful combination.